Welcome back to my YouTube videos. Today we're taking a look at week 9 bell work. Again, these bell works are assigned on Mondays and Tuesdays and they're due on Friday of the same week. So looking at week 9, this should be a review of skills that we've covered in the first few weeks of school, or even backtrack to things that you've learned in the elementary. Taking a look at the first problem, it says find an equivalent fraction for each. Remember to use the same rule in the numerator and denominator. So if I take a look at the fraction that I'm given first, I notice that they give me 5/6. They're trying to get me to find an equivalent fraction. Well, one way of doing that might be with a model. We could quickly sketch out 5/6. Notice my denominator is a 6. That really tells me that I want 6 equal parts. 1, 2, 3, 4, 5 lines will give me 1, 2, 3, 4, 5, 6 parts. Now I want to start with 5/6 of those pieces. So I would shade in 5 little parts of the whole bar. So I have 5/6 shaded. Well, they're asking me to write an equivalent fraction, and in order to do that, I could try a couple things. I could decide to take these pieces and split them into smaller parts, right? So one way of doing that might be to split them right down the middle. And I've just doubled the number of pieces I have, and they've gotten smaller. So I might count up now and notice what I have. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 little shaded pieces out of how many total possible? Well, I've turned it into 2, 4, 6, 8, 10, 12 equal parts. So we might say there are 10 shaded out of the 12 possible. 10/12 is one equivalent fraction. You could also look at this another way. Lots of students remember finding equivalent fractions in the elementary, where you would find some rule to use in both the top and the bottom of the denominator. So perhaps I wanted to say 5 times 2. I want to double the numerator, but as soon as I double the number of pieces I have, I just doubled the number of pieces I started with as well, or the total. And again, the pieces are getting smaller. We just saw that in our model. So 5 times 2 would get me 10, and 6 times 2 would get me the 12. So using equivalent fractions, we could also think about multiplication of the same rule on the top and the bottom. And you might say, why does that work? Well, that's a great question. If we keep it fair on the top and the bottom of our fraction, you'll notice that I'm actually multiplying by 1. 2 halves is really the same as 1 whole. And whenever I multiply a number by 1, it doesn't change its value. So I can really choose any numbers. I can multiply the top and the bottom by 3. So multiplying by 3/3, that's the same as multiplying by 1 whole. Let's take a look at the next one. So here I have 3/4. We could try this model strategy again. So I'll draw a quick sketch of a bar model, and I'm going to break it into how many parts? Look at that denominator. It's telling me to make 4 pieces to start. 1, 2, 3, 4 equal parts. But I only have how many of those pieces at this point? Well, looking at the numerator, I only have 3 of those possible fourths. 3/4 is my bar model and the fraction I'm starting with. Well, similar to what we did on the last one, as long as I split all of these into equal numbers of parts, I'll get an equivalent fraction. So last time I split them down the middle, right? I turned them into twice as many pieces, but they were definitely smaller parts. I'm going to try the same idea, but maybe I decide to split it differently. Maybe I decide that I want to break each of these into 3 little pieces. So, hi-ya, little tiny karate chops. I have 1, 2, 3 little tiny pieces here. And I can do it again. 1, 2, 3 little tiny pieces. And I can do it again. 1, 2, 3 little tiny pieces. And even though this is missing, we really might want to show this idea of, oops, I just did that wrong. I'm sorry. We really might want to show how many total small parts we would have had, how many equivalent parts we have in the whole bar. So taking a look at the entire bar, I now have 3, 6, 9, 12 total parts. So there were 12 parts to start this bar. And how many are shaded? 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 shaded out of the 12. 9/12 is an equivalent fraction. And you might say to yourself, well, I don't know about that bar model idea. That's not something I've seen before. So you might try it differently. You might say, hey, let's multiply the top and the bottom of our fraction by the same rule. So maybe I decide to multiply them both by 3. If I multiply the top times 3, I better do the same thing to the bottom. I'll end up with 9 over 12, 9 twelfths. There's another way of getting there. Remember, we have to use the same rule in our numerator and denominator to make things equivalent, also equal. Let's take a look at the next problem. Here we have whole numbers and we're doing some addition. It says find the sum. Oh, well, this is just a big clue to me that sum represents the result of an addition problem. So we've learned to do this primarily by starting in the ones column. The column farthest to the right in this case is the ones. So I'd say 8 plus 1 gets me 9 ones. I'll keep those 9 ones in the ones column. Now I move to the tens place. I have 9 tens plus 8 tens gets me 17 tens. Well, I might keep 7 of those tens and trade a group of 10 in for 100. So now I have 300. 300s plus 100 gets me 400s. I'll just keep those 4 hundreds in the hundreds place. There's no regrouping to do. Next I'd move to the thousands place. 7 thousands plus 2 thousands. 7, 8, 9, oh yeah, I'll get 9 in the thousands place. I'll move to the 10 thousands place. 3 groups of 10,000 plus 7 groups of 10,000 makes 7, 8, 9, 10. Makes 10 groups of 10,000. Usually what we do with this is we'll keep the 0. We'll trade in all 10 of those groups for one group of 100,000. So there's a regrouping that we show in our algorithm. Next I have 6 plus 3 plus 1 more. Well, 6 plus 3 is 9 plus 1 more is 10. This number is really difficult to read. The way it's written, there's not much notation there to help us out. So what might we add? What might we include to help with our legibility? Oh, if you notice, there are commas in the original problem. Those commas are helping to signify place values. So I might move over 1, 2, 3 places and place a comma, and go again 1, 2, 3 places and place another comma. After doing that, this number gets a little more reasonable to read. So if you notice, this is the ones, tens, hundreds, thousands, 10,000, 100,000s, millions place. I have 1,009,479 as a final answer. That's the sum. Let's see if we can sneak ahead to this next word problem. Here it says, Kathy is baking cakes. Each cake requires 1/12 of a teaspoon of vanilla, and she has 9/12 of a teaspoon. How many cakes can she bake? Looks like there should be some different punctuation in there to me, but I am no writing teacher. So let's go ahead and focus on the math. Well, how much does it take for each cake? If you notice, they said that each cake requires 1/12 of a teaspoon. Well, that's great, but how much do I have to start with? How much vanilla is there to work with? Well, we dig in a little bit deeper and I noticed that we had 9/12 of a teaspoon to start with. Well, I could probably draw a picture of this. It says I could draw a model if I wanted to, or I could use keep, change, flip. That's kind of hinting at what operation I have to use. Well, let's think about this. I have a bottle filled with vanilla, and I have 9/12 of it. This is what I'm starting with, and I kind of like to signify that in my word problems. When I can find the start, that's a helpful piece. So I want to split this into 12 equal parts. I'm not sure if I made my bar long enough, but let's give it a go. With 11 lines, I should be able to make 12 equal parts. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and clearly I made my bar a little too long, so I'll erase a tiny bit. Let's double check that I have 12 equal parts. 2, 4, 6, 8, 10, 12. Double check yours, make sure that it's working well for you also. Well, I don't have all 12 12s, do I? I don't have a full bottle of vanilla. I only have 9/12 of a bottle. So for that reason, I'm going to shade in 9 parts. Oh, I think I overdid it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10/12. That's not what I have. I have 9/12. This looks better. So 9/12. Well, how much does it take each time to bake a cake? Well, each cake requires 1/12. So I'm breaking this into a group of 1/12. There's a group. I can make one cake. But I need another 12 to make a second cake. Boy, I must really like baking, or at least eating cake. Could I do it again? Yes. And so on. And another. every single one of these 12ths that I have to work with will help me make a cake. So next I would have 6, or 7, and 8, and 9. I don't want to continue counting here because, again, I didn't have a full bottle of vanilla, so I'm only able to make 9 groups. Really, when I talk about grouping, or how many are in each cake, I'm splitting them into 12ths. That's a division operation. We're actually finding a quotient of some fractions. Well, when I'm done, I came up with 9. 9 is an answer. But that's kind of an embarrassing answer, let's be honest. This was a word problem. When they give you words, give them words back. So if I say good morning, you'd say good morning, Mrs. Schumann, because that's just a respectful thing to do. It's a whole lot nicer than grunts. If you take a look, I'm trying to answer how many cakes can she bake? I just did a reread of the question. Oops, trying to find a color we haven't used up there. Here's the question, how many cakes? Sometimes I'll circle my question and kind of put a question mark next to it. That's what I'm trying to solve. And if you've talked about Math in Focus in the elementary, they may have even shown you to write the sentence first. You might write, Kathy can make blank cakes, and then fill in the blank when you're done. Well, I'm okay with finding this answer of 9, and I know it belongs to the number of cakes I can make. We have a final answer. If you take a look, it also suggested that I could use something called KCF. Now, some of you have learned that that's called FCF, freeze, change, flip. But the problem I've been running into is students sometimes get these letters for F, freeze, and F, flip confused. They get them flipped around. Oh dear. So no one wants to be confused about that. So for that reason, I might change your thinking to keep, change, flip. And actually, this is a reciprocal method. So they might ask you one day to use reciprocal multiplication to solve. That is the same as a KCF. Or those of you who can keep the letters straight, FCF. Let's try it. What if I were to take the first fraction, the amount I started with, and freeze it? Well, that would make it look the same. If you put something in the freezer, it usually comes out a little bit frostier, but looks pretty the same. Well, next I need to change from division to its opposite or inverse. The opposite of division is multiplication. And if they tell me to flip the second fraction, I actually could think of it as a reciprocal. The numbers are switching positions, so the 12 in the denominator moves to the numerator, and the 1 in the numerator moves to the denominator. I'm really ready to multiply. I could multiply straight across, but 9 times 12 gets mighty big, and I see something that we might want to consider instead. Something we haven't talked about a lot this year, but I sure hope you learned in the elementary. Some teachers call this the Band-Aid method. Some people call it the boo-boo method. Some people call it the butterfly method. I call it cross-simplifying. Do you see how these numbers across from each other are both the same? They wouldn't have to be the same, but they would have to share a common factor to simplify them. Well, 12 and 12, because they're the same number, could both be divided by, 1 is nice, but it wouldn't change the numbers. 2 isn't bad, they're both even. 3 would work, 3 goes into 12 nicely. How about 4? Yep, 4 goes in there a whole number of times. 6, oh, 6 is good. But look, 12 goes into both. I could divide both of these numbers by 12. This is called cross-simplifying. So I'm trying to find a common factor, the biggest one, also known as the greatest common factor, so that I can make my numbers a little smaller when I'm working with them. Well, how many 12s go in 12? Just one group. How many 12s come from this 12? Just one group. And if you notice, I've really made those numbers a lot smaller to work with. You could always check for cross-simplifying going the other way. This 9 and this 1 are diagonal from each other. They are across. And if you notice, we've made 2 Band-Aids, we've made some boo-boos, or we've made a butterfly, or we've checked for cross-simplifying. But if 1 is sitting here, that's really as low as a whole number as we will go when we're simplifying. So as far as simplifying, we're done. The next move would be to multiply across. So I have 9 times 1 and 1 times 1 on the bottom. Well, I might even rewrite the fractions just so that you can see where these numbers are coming from. This would be a rewrite step. 9 times 1 is 9, and 1 times 1 is 1. And if you take a look, my answer looks a little different, doesn't it? Hopefully you're thinking to yourself, whenever I see a number written over 1, it's equivalent to the whole number in the numerator. So this 9 over 1 is equivalent to 9, which is perfect because that's an answer we got, 9 cakes. I'm going to go ahead and clear this for us so we can fast forward to some long division. I see a long division coming at us, and in fact it says find the quotient. I hope you're getting more comfortable with this terminology. What do you think quotient means? We've talked about it before. Quotient. And I notice a long division sign over here. I'm thinking it has to do with division. In fact, it has to do with the result of a division problem. We are going to try using the algorithm for this problem. So the algorithm would tell us to follow some important steps. We sometimes say dad, mother, sister, brother, or does McDonald's sell burgers? Either way, you can remember these steps in order, so just a funny little mnemonic that kind of sticks with your head, I hope. So the first thing we want to do is think about dividing, but I don't know about you, my facts of 21 aren't that great. So I'm going to try counting by 21s just to get a good start on what I might need to use for my long division. Let's count by 21s. 21 times 1 is 21. 21 times 2, well that's like doubling it, isn't it? 21 plus 21 would get me 42. I could add another 21 to this. If you remember when we talk about multiples, we keep adding the same thing every time. So I don't know about adding 21, but I could add 20 and one more. 42 plus 20 is 62, plus one more is 63. I could try it again, add 20 plus one more. 63 plus 20 is 83, plus one more is 84. I'll try a few more with you. 84 plus 20 is 104, plus one more, 105. Let's try again. 105 plus 20 is 125, plus one more would get me 126. And I shouldn't need anything too much bigger, but we'll just try a couple more because I'm liking this number pattern, or this mental math that's happening here. So next I have 126 plus 20. Let's see, that's 146, you might say, plus one more makes 147. I am seeing some patterns happen here. If you notice, the preceding numbers are 2, 4, 6, 8, 10, 12, 14. That's kind of cool. And if you look, the numbers at the back, 1, 2, 3, 4, 5, 6, 7 are increasing by 1 each time. There is a kind of cool pattern happening here that I kind of like mathematically. All right, let's go ahead and dig into our long division. I think we have enough work written down that maybe this can happen without much difficulty. First step, D, divide. 21. Does it go into 3 nicely? Well, you might say it could, but you get a fraction or a decimal, and we're trying to get whole numbers right now in our quotient. So I would say no. We'll place a 0 there as a placeholder. Next you say, does 21 go into 34 or 34 hundredths? And in fact it does. I could take my 34 hundredths and break them into 21 equal groups. So let's think about how many times I could do that, or how many hundreds would fit in each group. So I'm going to look at my multiples. I'm going to get as close to 34 without going over. Oh, right here, this is as close as I'm going to get. 42 is too big, 21 will work. Well, this is the same as 21 times 1. So that number goes in my quotient. 1 times 21, I next get to multiply, is 21. And next it says subtract. Does McDonald's sell? Yep, S for sell or S for subtract. 4 take away 1 leaves me with 3 in the hundreds place, and 3 take away 2 leaves me with 1 in the thousands place. I now have 13 hundredths left to work with, or 1,300, with some remaining pieces here. Next, after subtracting, you might go back to this chart which tells us to bring down. Well, there is a number to bring down. It's a 7. So I'm going to treat this like 137 tens, or I could just say 137 divided by 21, some people like to say. And I'm going to look over here at my chart and see how close we can get without going over. Trying to get close to 137 without getting too big. Ooh, look right here. 147 is really close, but a little too big. So I'm going to go for this, 126. So how many 21s was that? 1, 2, 3, 4, 5, 6 of them. So if I put a 6 in my quotient, 6 times 21 should get me 126. I just got that from these multiples that we wrote out early in the problem. When you subtract, 7 take away 6 leaves me with 1, 3 take away 2 leaves me with 1, 1 take away 1 leaves me with nothing, and things are looking pretty good. I noticed that my remaining parts here are smaller than my divisor. This is super. But there's another number to bring down, so for that reason, let's bring down the 9. I now have 119, and I'm going to split it into 21 groups equally. So I'm going to get as close as I can in my multiples list to 119. Do you see something that will work? I hope you're noticing that 105 is pretty darn close. So we're going to use this to help us out. I'm going to figure out what multiple that is, or how many times 21 goes into 119. 1, 2, 3, 4, 5. Looks like 5 times. That 5 goes in my quotient, and 5 times 21 is the same as 105. I know that because I just looked at my multiples list. And when I subtract, I'm left with something that looks like this. Now, this actually could be a final answer if I know how to write it appropriately. So a lot of you like to use the evil R word. Well, that was really cool in the elementary. We don't use that as much in the 6th grade. Actually, I would really like to see you write this as a mixed number. So let's talk about the ring of fire. It's so dangerous, but awesome. So let's try to put these numbers in order so that we have a whole number with a fraction behind it. Notice the whole number of groups comes first, 165. The remaining pieces become the numerator. They're how many little parts I have left over, but I was really trying to make groups of 21. So it's 14 over 21 as my fraction. This looks awesome. I'm thinking about circling it. Someone in class today said, "Circle it, Mrs. Schumann, call it your final answer." And I said, oh, hold up. Whenever I have a fraction, I might want to consider simplifying. So can you look for 14 and 21 on your multiplication chart? Or can you think of a number that is a common factor for both? Something that divides nicely into 14 and 21 a whole number of times. Oh, they're not both even. Don't try 2s. How about 3? 3 goes into 21. Oh, not very nicely into 14. How about 4? Oh, no, only one of those numbers is even. Don't need to try 4s for 21. How about 5? No, neither of these numbers end in 5 or 0. 6? I don't see them in the 6th row. How about 7? Oh, there's 14 and there's 21. I could divide both of these numbers by a common factor of 7. In fact, that ends up being their greatest common factor. So, I have this whole number. It comes along for the ride. I haven't changed anything about it. I'm just rewriting it in a simplified way, right? A simpler way. So 7 goes into 14 2 times. And 7 goes into 21, 7, 14, 21, 3 times. And if you double check, we can't simplify any farther. This is a final answer. 165 2/3. Next we have a decimal problem coming at us, and it says find the sum. I hope this word sum sounds somewhat familiar. Pun intended. What does it mean to find a sum? Here's a hint. I notice that there's addition. Oh, we're looking for the result to an addition problem. So to do this, they give me a hint. Line up your decimals. Lots of us are having trouble with this when the numbers don't seem to have the same number of digits. This one doesn't seem to have that problem. But just in case, let's put a decimal on top of a decimal. This first number, the 85 and 560 thousandths, has 2 numbers out front. It has an 8 and a 5 before the decimal. And it has 3 numbers behind it. It has a 5, 6, 0. The second number, notice I have the decimal placed first thing because I want it lined up with addition or subtraction of decimals. It keeps our place values aligned. In front of that decimal I have 2 places. 1, 2. And behind it I have 3 places. Let's fill in the numbers. In front of the decimal I see a 3, and in front of that I see a 5 in the tens place. Let's look behind the decimal. I notice that I have a 339, 339 thousandths. Now am I adding or subtracting? That word sum told me I better add. So let's go ahead and talk about adding these together. Well, just like we would for a whole number, we'd like to start in the right-hand column. That's what the algorithm would tell you to do. So it's kind of like the strategies, those quick tools that we use to try to get to a final answer. If you look, I have the thousands place back here. I have 0 thousandths plus 9 thousandths. 0 plus 9 is 9. Next I move to the the hundredths place. I have 6 hundredths plus 3 hundredths. That gets me 9 hundredths. Next I move to the larger place value on the left, the tenths place. 5 tenths plus 3 tenths gets me 8 tenths. Notice these decimals, they're aligned for a reason. They're keeping my thousandths with my thousandths, my hundredths with my hundredths, my tenths with my tenths. This decimal is critical and it needs to come straight down to maintain my place values. Let's move to the ones place. This is called the ones. I have 5 ones plus 3 ones gets me 8 ones, and next I have 8 tens plus 5 tens gets me, let's see here, 8 plus 2 would get me 10, plus 3 more. 10 plus 3, 13. I get a result of 138 and 899 sorry, not 10 thousandths, 138 and, when I get to that decimal, 899 thousandths. Tenths? Probably shouldn't do it that way, should I? How about this? Tenths, hundredths, 2 places, 2 zeros, thousandths. Good. And that was possible because our decimals were lined up. We always want to remember that with decimal addition or subtraction. I will also point this out. It's very possible if they would have given me this problem without the 0 at the back here, would that still have the same value? In fact, it would. So if that had happened to us, we would probably just fill in a placeholder. Let's take a look at the next problem. So moving to the back side, let's see what we have. I can't get to the back side, but I'm trying. Here we go. Oh, this one's very similar. It says find the difference. And I really believe that you're going to be very capable of setting this up. The thing that I'd be concerned about is a little bit of regrouping that sometimes we run into as 6th graders and get a little bit nervous about. So let's go ahead and work on finding the difference. Well, what do we think difference hints we need to do? Oh, we're going to subtract. I'm going to find the result to the subtraction, and I'm going to line up the decimals. It gave me that hint again. Let's go ahead and stack our decimals first thing. The first number has 2 digits out front, and it has 1, 2, 3 digits behind the decimal. Our next number has 2 digits out front and 3 digits behind the decimal. That won't always be true, but for today's purposes, they made it kind of nice, didn't they? Let's go ahead and fill in what we have here. So looking at the first number, I have 65 wholes before the decimal and 440 thousandths. Again, that 0 might not be on there in original problems, and then we would just go ahead and use a placeholder. Take a look at this next number. I have 43 wholes and 879 thousandths. Remember, difference means let's subtract. So we're doing a subtraction here. If I use the standard algorithm, you know that we might run into a challenge. First step. If I have 0 thousandths and I want to take 9 from you, you'd end up with a -9 thousandths. So that's a lot to think about before we do, integer subtractions. So for that reason, let's go to the nearest neighbor. You've learned to regroup. We'll leave 3 here in the hundredths place, and we take one of those hundredths and break it into smaller pieces. I now have 10 little tiny thousandths. Well, if I had 10 thousandths, take away 9 of them, I'd be left with 1. Here I have 3 tenths. Darn it, I did it again. I have 3 hundredths. Take away 7 hundredths. And that's going to be a problem, isn't it? We haven't learned how to do those negative subtractions yet, or those negative numbers as results yet. So for that reason, we'll go to the nearest neighbor and leave him with 3 in the tenths place. Well, we just gave him a group of 10 next door, so 10 plus 3 gets me the 13 I need. 13 take away 7. Well, 7 plus 7 is 14, a little too much, so let's drop that down. I should be left with 6. 6 in the hundredths place. Next I have 3 tenths, take away 8 tenths. Again, I'm going to get a negative result if I do it the way it's given, so I'm going to move to the nearest neighbor, which happens to be in the ones, leave him with 4, and I say thank you for the group of 10. 10 plus 3 gets me 13 tenths. 13 tenths take away 8 tenths. Well, I know 8 plus 4 is 12, so I'm pretty sure I'm going to have a 5 left over here. My decimals, they're pretty critical with addition and subtraction. They help me line up place values, even though sometimes I misspeak and I tell you the wrong thing. Okay, so we're going to bring that decimal straight down into my answer. Next, 4 ones take away 3 ones. Well, 4 take away 3. That leaves me with 1. And here in the tens place, I have 6 tens, take away 4 tens, I'll be left with 2 tens. I have a final answer. Can you read this for me before I say it out loud? Think about what do we say when we get to this decimal. What word do we use? And think about where this number lands. I notice that if I cover up the back of it, I have 21 wholes. And at the back of that, I have 1, 2, 3 place values. Oh, tenths, hundredths, thousandths. Let's give it a try. 21 and 561 thousandths. That's a final answer. There is a way that you could be checking these decimal problems. We could work in reverse. What's the opposite of subtracting? Maybe you'd say adding. So we could go ahead and add our result, also known as our difference, with this number that we subtracted. And if it works out correctly, it should take us back to the original or our starting value. Let's move on to another review problem. This one involves LCM, also known as least common multiple. It is the smallest multiple that both of these numbers share. So there are a couple ways to do that. My hints to you today, we could try a multiples list where we count by 12 and we count by 15. The thing that I'm concerned about, I'm not sure I know my multiples of 15 really well. So we could also try something else called factor trees. Let's go ahead and try that for this problem. I know a lot of my students like factor trees. That would be another reason to try it. So let's go ahead and break our 12 and our 15, which are both composite, into some prime numbers. Well, 12 is the same as 4 times 3. And if you check your chart or you think back, 3 is considered prime. It can't be broken down anymore besides 3 and 1. So this 4, it's not prime, it's composite. We're going to break it down into two factors, 2 times 2, which happen to both be prime. How about 15? That's the same as 3 times 5. And if you check your chart or think back, we know 3s are prime. We circled it on our other tree. What about 5? Oh, yeah, the only way to make 5 is 1 times 5 when we're talking about factors. So this is also prime. With all good trees, we should chop them down. Okay, that sounds like I'm the Wunzler, so that sounded kind of harsh. Instead, let's go ahead and organize our prime numbers. 12 is the same as 2 times 2 times 3. I'm only recording those prime numbers I got. 15 is the same as 3 times 5. And if you remember looking back or thinking back to our first unit of study, I'm looking for something that they have in common. So do they share any common factors? Oh good, they both have a 3. That's helpful. Do they share anything else? No, I just found the greatest common factor. The biggest number that divides nicely into both is 3. Hold up, stop the bus, that's not what we wanted. We were looking for the least common multiple. So another way to get there is to use the greatest common factor and then multiply it times its extras. GCF times extras. That's how I'm going to find my LCM, or least common multiple. The least common multiple is the smallest number that they both can multiply to. Well, the GCF is 3, and the extras are the things that didn't have matches over here. So the extra prime numbers for my tree is 2 times 2 times 5. I can really choose any chunk of these to multiply at a time, but I really prefer to multiply 2 numbers at a time. So 3 times 2 gets me 6, and 2 times 5 gets me 10. I still need to multiply there. Kind of solving this like order of operations, aren't I? Kind of like a funnel, kind of moving down the page, kind of making pizza math. I'm hungry, that was a bad idea to say. 6 times 10 is 60. When you are done, you will find the least common multiple. The first multiple that both numbers share is 60. I'm going to let you take a look at the next problem, and I'm not sure I'm going to solve it for you, but I'm going to give you a hint. You could use a T-chart, or you could use factor trees. And we just used factor trees, didn't we? So instead of taking the GCF times extras, you're just going to stop when you find, the GCF. So I do suggest trees on this one, unless you're really amazing with your T-charts and your facts. I think it would be wise to break 54 and 32 into prime factorizations first. Let's take a look at this last problem. Oh, they ask us for 2 things today. Find the mean and range of the set of numbers. I gave you some hints off to the side today. So mean, some of you remember it stands for the average. So in fact it says that in my little hint off to the side. Mean is the average. So pretend that these are all different quiz scores, or these are all different numbers of goodies you were given during the week. We want to find the average. So kind of like a middle value, if you will. To do that, it says add them all up. Oh, we have to find their sum. And when we're done, divide by how many you have. So after we find the sum, we need to divide. So let's give this idea a try. Well, we could try some number bonds here. I notice 8 and 2 is 10 when I add. I notice that, how about this? 4 and 6 is 10. I notice that 3 and 2 gets me 5, and this 9 didn't really have a buddy, so I'm just going to go ahead and add these up. We're going to continue adding to find the final sum. Just trying some number bonds, putting some numbers together that give me some valuable tens or something that I like to work with. Well, I can handle this a couple different ways, but I see I have a 10 and a 10. 10 plus 10 gets me 20, and here 5 plus 9 gets me 14. And before someone shouts, what about PEMDAS? What about order of operations? I hope you remember that addition is commutative. We can rearrange it all day and all night, and we'll still end up with the same result if we're careful. So next I have 20 plus 14, which gets me 34. Please don't tell me this is your final answer. I realize that's your final sum, but that's not a number in between 8 and 3 and 6 and 9. It's not a number that's in the middle of those, is it? So I'm looking for something that's going to land as an average somewhere in between. So for that reason, it says divide by the number of numbers you have. How many numbers were we given? Well, I have 1, 2, 3, 4, 5, 6, 7 numbers in the set. I'm going to take 34 and divide by 7. 34 was the sum, and I'm breaking it into 7 equal parts. I'm trying to figure out an average. 7 times, let me think. 7 times 5 is 35. That's a little too big, isn't it? So I think 7 times 4 will work. Another way would be to say 7 doesn't go into 3 nicely, but it does go into 34 a whole number of times. So 7 times 4 is 28. I'll let you do a little regrouping here and subtract. 14 take away 8 gets me 6. 2 take away 2 gets me 0. I'm really ready to write this as a mixed number. We saw something like that on an earlier warm-up, taking our long division and turning it into a mixed number. So how many whole groups did I make? 4. And how many leftover parts do we have? 6. Out of how many did we want in a group? 7. 4 and 6/7 is the mean, or the average. Now that was only one part of this mean problem, okay? So instead, we need to go back to the original problem and make sure we're doing the second part, which says find the range. There's a hint over here for range. If you notice, I circled the highest and the lowest values, the minimum and the maximum, and they're subtracting to find what we call the range. So I'm trying to figure out the distance between the highest and the lowest values. Well, I didn't put these numbers in order today, and I probably could have, but I think we'll be able to find the high and the low pretty quickly. So what's the minimum, the tiniest number you see? Oh, I see a 2. That's pretty small, isn't it? I tried to change colors. That didn't work for some reason. 2 is the minimum. Do you see the maximum, the biggest number? Oh, in this case, 8's pretty big. Ooh, but 9 is bigger. I'm going to use the maximum minus the minimum. So 9 take away 2 gets me, let's count backwards, 8, 7. 7 is going to be the range. That means that there's just a distance of 7 between the numbers in my data set, or in my set of numbers. There are 2 answers here. There was a part A and a part B. The mean, we had to find the average. So first we found the sum, the total, and then we divided by the number of numbers we were given. We got something kind of weird. We got a mixed number. That does happen quite a bit. Next we had to find the range, and I didn't put the numbers in order as they did, but I was still able to find the maximum and the minimum and do some subtraction. I hope you've learned something new, or maybe reviewed a skill that you had forgotten working on this bell work for week 9. Make sure that you have it ready for Friday.